Okay, so we'll get started. A couple of quick announcements. So I extended the deadline for homework 2. So you should have seen that in your email, and then I will send out homework 3, which I've already written it, but I'm going to slightly change the deadline for that to accommodate your schedules. Lecture 5, the video crashed in the middle of the class. So if you look at it online, after there's something happened, a glitch in the middle of the class, and then Zoom crashed. And so then the video, you can hear me talking, but not see the video. So do you want me to re-record it? Are the videos useful? Yes?
Is this last lecture?
Pardon?
Is this Monday's lecture?
No. Monday's lecture is fine, as far as I know. This was lecture 5.
Okay.
So I can re-record it, it just takes an hour and a half of my time.
I think you're also talking to people who were there. So.
Right. Well, anyway, I will record it, and those videos I put them up on YouTube as well. So okay, last time we were talking about the Kadanoff block spin construction. This is a prelude, a simplified form of a renormalization group. So this was historically how renormalization group had its roots. In fact, Ken Wilson's paper on renormalization group in 1971, its title, I don't remember the exact title, but it was something like, a dynamical systems approach to Kadanoff's block spin construction. So he literally had Kadanoff's name and the block spin idea in the title of the paper. I do not understand why the Nobel Prize went to Ken Wilson. Certainly deserved it, absolutely, for sure. I do not understand why it only went to him, though. I think there was 2 other people for whom it could have gone, and so, but there you go. So what was Kadanoff's big idea? So Kadanoff wanted to explain the data collapse scaling laws that I'd shown you evidence for earlier in the class, and he understood that they happened along with Ben Widom, who wrote a famous paper on this in 1965, preempting Kadanoff's paper. But Kadanoff then went on and figured out what was the origin of the data collapse scaling. And his idea was basically the following. If you look at the bottom of the right-hand panel here, so here is a blob of, say, upspins in a sea of downspins near a critical point. So you have a blob whose dimensions are vaguely of order the correlation length, and the lattice spacing is written there in gray. And so what he said was, well, why don't we take a bunch of these spins, which are on the scale of angstroms, and why don't we just group them together? And the grouping them together produces what he called a block spin with size L times A. So A is the lattice spacing, L was the number of the dimensions in units of the lattice spacing. And then because the correlation length is diverging near the critical point, that means it's much bigger than the lattice spacing. And so I can choose, any arbitrary grouping of spins LA as much as I want, as long as it satisfies the inequality I've shown over here. And then what Kadanoff said was, well, if I've got these block spins, what is they're all correlated, strongly correlated, because they're within a correlation length of each other. So they ought to behave essentially like one variable. If they behave like one variable, then we can call that a block spin, an effective spin. And what do we think is the Hamiltonian for that block spin? And his idea was that the effective Hamiltonian for these block spins had the same functional form as the microscopic Hamiltonian. So if you start off with a nearest neighbor Ising model with electronic dipole moments on the lattice sites, when you make your block spins, they also have nearest neighbor interaction. So nearest neighbors on microscopic, nearest neighbors on the block spins, and from that then you know that the functional form of the Hamiltonian is the same as the original one, but with new coefficients representing the effective interactions between the spins and the effective interaction between the spins and an external magnetic field. So he made that first assumption that the block spins have the same functional form. And then the second assumption he made was, well, if I know there's going to be some new coupling constants that act on the scale of the block spins, let's just assume that they will depend on the scale by the formula written down at the bottom of the right-hand page, that they scale as a power law with this block spin size. And that power law has two exponents, one for the coupling, but for the temperature, one for the external field. And why does the temperature change? Well, that was the argument which we made over here. So what we know is that the physical correlation length, and now look on the left panel, can be written in units of the block spin size, so psi times LA, but in units of the lattice spacing size, it's just what I call psi1 of A, so L is equal to 1, just a single spin. And then what that means is that then the correlation length in units for the block spins, the effective correlation length for the block spins, is actually smaller than the correlation length for the individual spins. And because it's smaller, that means that the block spins think of themselves as being further away from TC than the microscopic spins. So the microscopic spins, as you go towards TC, the correlation length is getting bigger. So as you go away from TC, the correlation length is going smaller. So when we see that the block spin correlation length is smaller than the original correlation length, we can interpret that as meaning that the effective temperature for the Hamiltonian governing the block spins actually describes a system at a temperature not the same as the original block spins, but at a temperature further away from the critical point. And so the temperature itself, the reduced temperature, then gets modified. And how it gets modified was Kadanoff's second assumption. So his assumption was, and we'll see that this can be justified by the normalization group method, that it scales as a power law. So that was his assumption. And then from that, what we did was we made a very judicious choice of L, because the scale of the block spins is arbitrary. And because it is arbitrary, we can choose any value that we like. So the value that we choose is the value shown over here on the left-hand panel, bless you. So we choose a value like that. And then what that means is that the first argument in the free energy as a function of t then becomes 1. And once that becomes 1, then essentially it becomes a function of one variable. And so we derived then the scaling form, the data collapse scaling form of the free energy. And the exponents that I've written down there, we've just defined alpha to be what those exponents are, but where those exponents come from, they are related to the exponents that were in Kadanoff's second assumption, the y sub t and the y sub h. So if you know those exponents, which we don't, but those exponents are related to observable critical exponents. And that was as far as Kadanoff could take it. So what we're going to do today is we are going to extend this to looking at the magnetization. We're going to look at the correlation functions. And I'm going to derive new scaling laws for the correlation length and a very important scaling law called the Josephson scaling law. And then next week we will start the renormalization group in its final form. So let's now consider the magnetization. So the free energy is not something that we particularly want to observe directly, but now we want to ask the question of how does the magnetization scale, the magnetization per spin. So we know that the magnetization is defined as 1 over kBt dfs by dh. Remember, h was defined to be h over kBt, so that's why there's this extra factor of 1 over kt there. And I have the functional form written up at the top of the page. And so what that means is that when I write down what m looks like according to the Kadanoff block spin construction, it's going to look like this. It's going to have these exponents. Then there's going to be a derivative of this scaling function, and there's two scaling functions, one above and one below TC. So the scaling function for the free energy per spin, and then that's h over t to the power delta, like that. And we know that this thing has to be some number of order unity times t to the power beta, because we know that the scaling function, we know that m near the critical transition scales as t to the beta, at least when h is equal to 0. And so what that means then is that we can then read off that beta must equal 2 minus alpha minus delta. So that relates those exponents, and so therefore I can write that m is equal to t to the beta times some new scaling function, we'll call it fm of h over t to the delta, and this fm, the scaling function for the magnetization, is in fact just the derivative of the scaling function for the free energy. Now we can understand the analytical structure of this function as follows. So there are some results on the asymptotic behavior of the functions fm, and then that's what we're going to discuss right now. So and what we're going to use the same trick that we saw very early on in the course. So we're going to use the scaling trick that we saw in our section on dimensional analysis. So what do we want? What's the problem? So the thing we want to understand is this. We know that when h is equal to 0, then m should go as t to the beta. I'll just say is proportional to it. And so that tells us that the scaling function fm at 0 must be just some constant. Whatever it is, it's just some numbers. But there's an issue, because what happens when t goes to 0? So what we know from mean field theory is that there's an interesting result from mean field theory. We already deduced that m goes like h to the power 1 over little delta at t equals tc, and in mean field theory, delta in mean field theory was equal to 3. So that suggests that we need to think very carefully about how we take the limit as t tends to tc for our scaling argument. So the question is, how do we see something like this? And what this thing was, this I told you was the breakdown of linear response theory. How do we see something like this breakdown of linear response theory in the Kadanoff block spin picture? So we can say, well, let's why don't we just set let's just set t equals 0 in our equation for m over here on the left hand side, but that gives you a problem. That gives you a problem for the following reason. There's two problems. One is that t to the beta then is equal to 0. And the second problem is that the argument of Fm goes to infinity. So both of those things are bad. So then we realize what must happen, and the answer is what we did in dimensional analysis. So what must happen to get a finite non-zero result what must happen is that Fm as a function of its argument must be a power law so that the factors of t outside Fm and in its argument cancel out. So that's what we need to have happen. Okay, so what power law do we need? Well, we can work it out. We can say, well, all right, so let's say that Fm of x scales like x to some power lambda, lambda to be determined. Okay, so let's suppose it does that. So then if I were to set m, I set t equals 0, but I keep h to be non-zero, then what that's going to look like is that's going to be t to the power beta. Then it's going to be h over t to the delta, and that's going to be raised to the power lambda, and we want that to cancel out. So this is going to be true as h is non-zero, t is going to 0, so that means that the argument is going to infinity. So this is going to be an asymptotic result as x goes to infinity, that it goes as a power law like that. Then what we need is that this thing then goes as t to the power beta minus lambda times delta times h to the power lambda. And what we want is that this thing should be independent of t. So we want t to cancel out. And so the way we do that is we require then that beta is equal to lambda times delta. And so this exponent, lambda, which we don't know, must then be equal to beta over capital delta. So if that's true, yeah, that's right. So lambda must be beta over delta. And then what I get then is that m at t equals 0 and h goes like h to the power lambda. And that means that lambda is equal to 1 over little delta. So that defines the critical exponent delta. And so then that tells us that this exponent capital delta must equal beta, must equal beta times little delta. So we have two deltas, a big delta, which is just a variable that we introduced from the Kadanoff block spin construction, and little delta, which is the observable critical exponent that tells us how the magnetization scales with h at t equals 0. So m goes as h to the power little 1 over delta, that we knew that we knew before, that we knew over here. And so now we've deduced that delta is not a new exponent, it's just the product. And so what that means is if we summarize this, and what I've just shown you is that m as a function of t and h is then t to the power beta times the scaling function fm plus or minus of h over t to the power beta delta. And that's and this is the result that we've predicted for the data collapse for the magnetization as a function of two variables. So that's our prediction. So we can compare this with what we did in mean field theory. What did we do in mean field theory? Well, in mean field theory, we discovered that h was equal to t to the 3/2 times some function which I called phi of m over t to the 1/2, and phi of x is equal to x plus 1/3 x cubed. So that's what we obtained when we did mean field theory. And so this says that that h over t to the 3/2 is a function phi of m over t to the 1/2. And this function phi of x, what's special about it is that it is a monotonically increasing function. Because it's a monotonically increasing function, that means it has a unique inverse. So therefore, I can say that m is equal to t to the 1/2 times the inverse function phi minus 1 of h over t to the 3/2. And in mean field theory, beta mean field theory is equal to 1/2 and delta is equal to 3. And so what I've just derived for you is that m is equal to t to the beta times some function, which I'll call fm, of h over t to the power beta delta. And this function fm is just this function phi minus 1. And so what we've derived on general grounds is indeed exactly what we saw as a special case in mean field theory. Okay, so now we really have a lot of confidence that we're on the right track. So now let's go away from thermodynamics, and now let's have a look at correlation functions. So what is our goal in this section? Well, what I want to do is I want to first of all I want to compute the correlation function for block spins. And what we expect to see, judging from what we saw for thermodynamics, is that we're going to get new scaling laws for correlations, which we will. And in fact, what we will see especially is we'll find a connection between thermodynamic scaling exponents. And spatial scaling exponents. Okay, so that's the idea. So let's try to see how we do it. So let me make a picture of a lattice. Okay, so here is our lattice, and our microscopic length scale, our lattice spacing is A like that. I've got spins on the vertices here. I'm going to imagine that I have made a bunch of block spins. So let's suppose I have some block spin like this, and then another block spin over here. So these are my block spins. I'm going to call this block spin I, and this block spin J like that. And I'm going to assume that their centers are separated by a vector like that, which I will call R sub L. And L is the block spin size. So this length here is LA like so. So that's the geometry of this. And so how do we define our block spin correlation function? Well, what we're going to say is, well, I'm going to have the correlation function as a function of R, and now R is a function of the scale L, and then it's going to also be a function of the reduced temperature at the scale L that I'm thinking of. And I'm not going to write it in explicitly, but also it will depend upon the external field, effective external field at the scale L. So remember that the game is this. You tell me what L is. That is the scale at which I look at the system. And I don't see anything else other than my variables defined on the scale L. So when I'm looking at block spins, all I see are the block spins. I see a big block spin here, and the whole thing might be pointing up. This whole thing might be pointing down. All of those spins are behaving together, and I only see the variables at that level of description. So when I want to define my two-point correlation function, this is then the correlation function of the fluctuations of the block spin variables themselves. So just in the same way that the original correlation function was this, but with the original variables, then my block spin correlation function is going to look like this. And this R here, so this is measured in units of A times L, because we're looking at the block spins variables. So for the block spins, all I know is that I see some spin variables on a lattice, and that lattice is a scale LA, not on the scale A that was the original one. Now, I'm going to assume that the correlation function is well defined. So if that's going to be true, then the distance between them must be bigger than the block spin size. So in order for this to be well defined, it shouldn't matter where I measure the vector from. So what I need is that R on the scale L is that magnitude is much greater than the lattice spacing A. And if I want to know what R is on the scale L, well, that is the vector R on the lattice scale divided by L. So if I have the distance between this spin and this spin as being R, then the distance between the block spins on the coarse-grained lattice, when I scale it by L, that distance gets smaller, and it gets smaller by the amount shown over here. Okay, so now the scaling question that we need to ask is what we want to compute is how excuse me, how is G as a function of RL, TL, and HL, how is this related to the original correlation function between spins, which is that? So what we're going to do is use our definition of what the block spins are, which I'm not going to repeat. So here is our answer. So first of all, we had a normalization factor, the magnetization of the spins in the block L. So that was equal to HL times L to the minus D divided by H, and that we define to be L to the power YH, and then because of that factor of minus D, that goes as minus D like that. So that's the first thing that we need to know. Then the second thing we need to know is we need to put in to our definition of correlation function, the definition of the block spins. So next, substitute into G for the block spins, the definition of S sub I, etc. So I'm just going to write it in, and then I'll go back and let you just see that it's true. So let me write it down. So G of RL and TL, I'm going to not worry about H for now. That's going to go like this: 1 over L to the power 2 YH minus D, then 1 over L to the power 2D, then the sum over the spins in block I, then the sum over the spins in block J, and then SI, SJ minus SI, SJ, the correlation length computed on the microscopic lattice. So where does this come from? Let's just go back, zoom back a couple of pages. So yes, here. So at the bottom of the page on the left, that's how I defined the magnetization per spin of the block of size L. So we basically average over the spins in the block, then we normalize by how many spins there were, and then we normalize by the mean magnetization of the spins on the microscopic lattice. And we did that so that the block spin itself had the value plus or minus 1 as its expectation value. So this was the main constraint that enabled this factor in the normalization. And that normalization then is written up at the top of the page. And as I just showed you, that normalization scales with L. That normalization scales with L by this formula over here. So now what I've got is these factors of L to this power squared times 2, that became because there's 2 powers of the microscopic spins in the 2-point correlation function. So this is ML squared. And then this factor of L to the 2D is because I'm summing over all the spins in block I, all the spins in block J, multiplying them together. There's L to the D spins in block I, L to the D spins in block J. And so this is the number of spins in each block. And then I'm summing and then over the correlation function of the spins. So going to my picture over here on the left, I'm taking each spin, it's in the block I, each spin in block J, correlating it with its counterpart in the other spin, in the other block, and that's the exact definition. And so when I say that the spins are very far apart compared to the block size, then those factors of L to the 2D in these sums will then just cancel out. Okay, so everybody happy with what this definition is telling us? Just saying take every pair of spins, one in block spin I, one in block spin J, look at their correlation function, normalize it in the way that we've defined, and that's going to be the definition of the correlation function. Okay, so what I'm going to say then is to our approximation, because RL is much greater than A, that means that that all the spins in in block I are approximately the same distance from all the spins in block J. And so then what I get is that G of R L and TL is then equal to L to the power L to the 2 D minus Y sub H times the correlation function of G of R and T, like so. And what I've assumed in doing that is that I can write that the sum over I in I, the sum over J in block spin J of SI Sj minus SI Sj, that is equal to L to the 2D times SI Sj minus SI Sj, where I'm taking that average in the center of each block. Correlation of a spin at the center of each block. And this thing over here, this then gives me L to the 2D. Okay, so then I know what R is, and so then I get that G as a function of R over L and T L to the power Y sub T, and for that matter, H times L to the power Y sub H. This thing is equal to L to the power 2 D minus YH times the original correlation function, like so. Okay. So that's a general form. And the basic trick, as we saw last time, was to choose a particular value of L. So the next step is we want to exploit our freedom to choose L. So what we're going to say is, well, why don't we choose L to be T to the power minus 1 over y sub t. Okay, so let's go ahead and do that. And now let's see what happens to our scaling function. So when we do that, then I'm going to invert the formula before. I'm going to say that g of r, t, and h then is equal to t to the power 2 d minus yh divided by y sub t times the function g of r times t to the power 1 over y sub t h times t to the power minus yh over yt, and then 1. Okay, so what did I do there? So I took the equation on the previous page, I inverted it, I substituted L goes as t to the minus 1 over y sub t in there, and once I do that, then the L disappears, and I just get t to the power minus 1 over y sub t, and then that gives me the exponent that you can see. Okay, so this is a function of 3 variables. And this now is a function of 2 variables. Okay, so what did we expect to see? So it's not quite this. We didn't expect to see something quite like this. So what we expected was something like this. We would have expected something like g of r, t, and h. What we would say is, well, it's going to go down like 1 over r to some power. So it'll be 1 over r to some power, which we don't know what it is. And then there should be some function of, well, there's going to be r divided by a length. So that length must be the correlation length. So something like that. That's what we would have expected to see, but that's not what we have. But actually it is what we have, but it's in disguise. So that's what we would have expected. So the next thing we can do is I can use a trick to beat down our formula into something that matches with our expectation. So how do I do this? Okay, so what I'm going to do is I'm going to say the following. If I have this g of r, t to the power 1 over y sub t, h t to the power minus yh over y sub t, and the third variable just has the value 1, I can, since I know that it's a function of those things, I can pull out this first factor. I can pull out a factor of this from the outside. So I'm going to write this as r t to the power 1 over y sub t, and I'm going to choose to raise that to a very carefully chosen power, the power minus 2 d minus yh. So I'm pulling that out, and then what do I have left? What I have left is a function that I'm going to call f sub g, which is then r t to the 1 over y sub t, h t to the minus y h over y sub t. So it's just a function of 2 variables. And so this is just a definition. This is just defining for me what I mean by this variable. Okay, so this defines for me what this function fg is. I've pulled out this factor. There's nothing to stop me doing it, But the reason I've done it is this factor of RT to the 1 over y sub t times this exponent at the front will then cancel out the factor of t in the front of my formula up here. So why did I do this? This trick enables us to cancel out the factor that I'm circling over here. Okay, cancels out that factor. So all the t dependence cancels out. And then what do I end up with after I've done that cancellation? After I've done that cancellation, what I've discovered is that the 2-point correlation function has then the following form. It goes as 1 over r to the power 2 d minus yh times some function, which I don't know what it is, that is a function now of just r t to the power 1 over y sub t and h t to the power minus yh over y sub t. And this is indeed a scaling law. This is indeed what we expected up here. This has the form of a power law function of r, some power law which is related to the exponents yt and yh that we don't know, and then a function of two variables. It depends on r times some power of t, and it depends on h times some power of t. Okay, so we're not done yet because there's more that we can say. So let me just put a box around this equation because it's a very cool equation.
So,
Yep, you have a question?
yeah, that's all okay.
You got it? You answered it yourself? Perfect. Okay. So I mean, I know the algebra is sort of weird because you're not used to seeing this before, but it just I mean you can just see that it works. Is there anything that is there a question of principle that you have, even if you didn't follow each algebraic step in detail? You okay?
Yeah.
Okay, great. Okay. So let's think about what we expected. So now think about what we expected. We expected the following. What we expected was that any functional dependence in fg, if it's going to depend on r, that's going to actually must be something that depends on r, which has dimensions, over another thing that has dimensions. The only thing that has dimensions at this scale is the correlation length. So we would have expected it to look like this. So we could have said, well, there's lots of things that have dimensions. It could have been LA, it could have been A, it could have been psi, it could have been the system size L, could have been the radius of the moon. Okay. Those could have been, but we know that we don't expect that to happen. Why? Well, because we already saw from mean field theory that what's happening is the correlation function decays exponentially at large distances, r greater than psi. So it goes as r over psi for large distances. For small distances, it goes as some power, distances smaller than the correlation length. So we already know that correlation functions are going to decay exponentially. And so what we would then expect then is if that's going to happen, since we've got a power law out in front, it must be the case that the thing inside must have some exponential dependence. It should therefore depend on the correlation length itself. And so we chose we chose psi because at large distances, correlation length goes like, correlation function goes as e to the minus r over xi, and xi is the scale that is growing with temperature. So remember that what we're doing here is we're looking at how these functions scale as we vary t. We don't care about the absolute numbers. We care about what is the asymptotic behavior, what are the singular behaviors as we vary t. All these other scales, the angstrom length A, the 3 times angstrom length LA, and things like that, the system size, a micron, okay? All of those things are just numbers. We don't care about those. The only thing that is varying with temperature is the correlation length. And so that's why that's the variable that goes in there. Now, if that's the variable that goes in there, then what that tells us is also something very interesting. So this then has a consequence, that what it implies is that t to the power 1 over y sub t must be scaling like the correlation length to the minus 1. Right? So over here, I have r t to the 1 over y sub t. We think that is going to be r over the correlation length as a function of t. And so therefore we can read off that xi to the minus 1 goes like t to the 1 over y sub t. And that then tells us that xi goes as t to the minus 1 over y sub t. But we also know that the correlation length diverges. Our name for that exponent is that the correlation length goes as t to the minus nu. That is the critical exponent for the correlation length. And so what we've just identified is that the physical significance of this mysterious number y sub t is that y sub t is equal to 1 over the correlation length exponent. So when we went back to Kazanoff's block spin hypothesis, right over here at the beginning of today's lecture and the lecture from earlier on in the week, what we had over here were these assumptions that the temperature scales as a power law in L for both for T and for H, and they scale as T times L to the power y sub T. And now we know that those exponents, if Kadanoff is right, then those exponents have physical consequences. In particular, y sub T is equal to the exponent 1 over nu, the correlation length exponent. Okay, so now we understand that, and so basically what that means is that that we can say that therefore we can write that g as a function of r and t. So basically that is going as some function of r over the correlation length, like so, and then it goes as 1 over r to the 2d minus y sub h exponent like that. And what I told you, and we're going to just define this, is that we can write this, we can define this exponent 2d minus y sub h. We're going to write that as d minus 2 plus eta. So why are we going to write it like that? Well, I'm going to show you later on that in mean field theory, we would expect that this correlation function decays with power 1 over r to the power d minus 2. So in 3 dimensions, that would be just like 1 over r. We'll just say the correlations decay at small distances like a power law, 1 over r, and then at large distances, they decay exponentially. But we know that that prediction from mean field theory is not quite correct. It's modified by this new exponent eta, which I told you about before, and so we're going to define it to have that number. So that means that in other words, this the exponent y sub h has a physical interpretation in terms of the critical exponent eta. And let me just remind you what that critical exponent eta is. If I sit at t equals tc, then what happens is the correlations as a function of k, values at tc, those go as for long wavelength, k goes to 0 as k to the minus 2 plus eta. Okay, so that's the definition of this critical exponent eta. It says if I take the 2-point correlation function in the Fourier transform in k space, that scales as k to the minus 2 plus eta. And if I take that in real space, so let's call this g hat, that says in real space, r at tc is that as r for r going to 0, basically r over r over d minus 2 plus eta. So this is the Fourier transform of that formula. So if I look at long wavelengths, or I look at large distances, in fact all distances, the correlation function is a power law for all scales, which basically means that the system is fractal, scale invariant, and the exponent is this combination I've written down here. Okay, so what I've shown you is that the conclusion is that Kadanov's assumption that there are 2 exponents TL describing how relative temperature varies with scale, and how the effective external field varies with scale. So those are the 2 exponents. His assumption that there were 2 exponents that describe the dependence on scale of the effective reduced temperature and the effective external field So his assumption leads to empirical predictions that explain what we observe experimentally. So we see that his assumption about these things, various power laws, I mean, I don't know the order in which he did this. I never asked him, but anyway, if you make that assumption, then it produces all these power laws for the thermodynamics, for the correlations, and so on. So it's a very good. It was a very good assumption. Okay, so now I want to move on. Can I explain the scale invariance comment? Yes. So when somebody says something is scale invariant, what they mean is that the functional form doesn't change if I change the scale. So all scale invariant functions have to be power laws. So if it is an exponential function, for example, or something with a scale, when I change the scale, the units, then the exponent, then the thing inside the exponential will change. If it's e to the minus r over xi, then I say I'm going to change the units, then it now becomes e to the minus 2r over xi, or something like this. So, but if I multiply distance by some arbitrary amount, that just cancels out as a factor if it's a power law function. So the functional form always stays the same. So that's called a scale invariant function, meaning that whether I look at it, with good resolution, or take off my glasses and look at it with bad resolution, it still looks the same to me. So that's called a fractal. Okay, so did I answer your question? At least with the brevity that is required. Okay, all right. So what I want to do now is I want to look at what happens for how does the correlation length itself scale. So we've already seen that the scaling, the correlation length scales with a power, scaling laws for the correlation length. And we've seen that the correlation length scales with a power nu or minus nu, it diverges. And that is related to one of these exponents y sub t that Kadanoff that Kadanoff wrote down. So let me make this. So let me say it like this. So far, and everything that we said, we were guided by the idea that the correlation length is the only important length scale in the problem. And that's true because it is the only one that depends on temperature. More specifically, the reduced temperature. So it's not quite true. So I'm going to give you a warning. So warning, this is not quite the whole story. So I want to just mention that now, and we'll come back to this a bit later. But what I want to do now is I want to show you that there is an interesting consequence from this. So what is the consequence? Well, let's suppose that I think about my free energy per spin, my free energy per degree of freedom, the singular part of the free energy per degree of freedom. I'm going to normalize it, since it's an energy, I'm going to normalize it by KT, it could be KTC, it doesn't really matter. So this thing over here is the singular part of the free energy per spin, and the number of spin scales with the volume of the system, and so therefore this is per spin, i.e. per unit volume. But the volume is L to the power D. So if I were to look at the dimensions of this quantity, then the dimensions of this quantity must be L to the power minus D. Okay, so this quantity is a quantity that scales as L to the minus D, but what L should I choose? So, and let me just make sure you remember, this symbol means dimensions. So if we believe this argument that it goes as L to the minus D, then this must in fact be psi to the minus D, correlation length minus D, and then maybe some corrections. So there might be corrections to this formula that look like this. For example, B1 over A over psi to the power sigma plus higher order corrections like this, where this B1 is some number of order unity, and this would be true. This formula over here would be true as T goes to 0. So as we go towards the critical temperature, T goes to 0, this correction term gets smaller and smaller, eventually vanishes. It's the correction to the leading scaling behavior. And the leading scaling behavior is this psi to the minus D. Okay, so that's nice. So what? So that then says that Fs over kBt, this thing scales then as psi to the minus D, and psi scales as T to the minus nu. So therefore this scales as T to the power nu times D. Okay, all right. So what? Well, let's now relate this to an experimentally observable quantity. So a good quantity that we know we can observe is the heat capacity. Say the heat capacity, it's a constant volume, which we know scales as T to the minus alpha as T goes to 0. Okay, so as we go towards the critical point, the heat capacity scales and diverges with an exponent alpha. So, but this heat capacity, C, is equal to minus T times d2F by dt squared. And since the free energy is going as T to the power nu D, then that must go as T to the power nu D minus 2. Okay, so the free energy goes as T to the nu D. If I take two derivatives of it, I get T to the power nu D minus 2. But that, by definition, is minus alpha. And so what we've discovered then is that 2 minus alpha must equal nu times D. So this thing over here, this thing must equal this. So therefore, 2 minus alpha is equal to nu D. And look at this. This is amazing. Okay, here, the left-hand side is thermodynamics. And this right-hand side is to do with the correlations. Tells you how the correlation function diverges. And so we have a connection now between the thermodynamic scaling laws and correlation scaling laws. And this is known as the Josephson scaling relation, or Josephson scaling law. Okay, I'll just do one more thing and then I'll tell you a funny story about this. Okay, okay. So let me. I want to get to this last scaling law, another scaling law. From the static susceptibility sum rule, static susceptibility sum rule. Okay, so again, we know that that chi sub t, that scales as t to the minus gamma, and we know that the correlation length scales as t to the minus nu. So then from the static susceptibility sum rule, you can derive that gamma over nu is equal to 2 minus eta. I'm not going to go through the proof of that. Okay, but if you just plug into the static susceptibility sum rule, maybe I'll even give you that as a homework exercise to do. You can easily derive that formula as well. So the point you're getting is that there's all these identities between scaling laws, between scaling exponents. We don't know what they are. We can't calculate them, but they all come out of this picture of looking at the effective interaction, the effective description of a system at different length scales, and we get all of these results. So what we've derived then is many phenomenological predictions just arising from the idea to look at the system at different scales. And so that's the good thing. So this is great. The bad thing is that we do not know how to calculate these exponents. We do not know how to calculate the things that we need to know, which are these exponents yt and y sub h. And that's what the renormalization group tells us. So that's what we're going to be doing next week. Okay, now I'm going to tell you a story. Okay, so here's the story. So when I was a graduate student in Cambridge, one of the, this was between 1979 and 1982. So the renormalization group had just been developed a few years before, and so we all wanted to learn a renormalization group. And the professors in the department, the Cavendish lab, thought this was a bit too newfangled and didn't want to teach it to us. So I said, okay, that's fine. We'll teach it to ourselves. So I started a study group, and we just started teaching ourselves a renormalization group from the papers that had already been written. Now, one of the people at the Cavendish at that time was Brian Josephson. Well, he's still there. He's retired now. But so Brian Josephson was there, and he was the one who developed this Josephson scaling law. Now, I've just derived it to you in 3 lines from scaling, but he didn't derive it in that way. He derived it from rigorous statistical mechanics, and he derived it as an inequality using various tricks. All these scaling laws that are equalities at phase transitions can be shown to be inequalities using thermodynamics and so on. And he went and he did that. He, probably as a graduate student or something like this. It was amazing. So I said, look, we're going to be having lectures this week about scaling laws, and we want to ask if you would give a lecture about your scaling law. So he said, well, I refuse. So I said, well, why? So he said, well, I refuse because my scaling law isn't as good as the other ones. So I said, well, what do you mean? He said, well, all the other ones, like the one I've told you, alpha plus 2 beta plus gamma equals 2, the Rushbrook scaling law, those are always true regardless of dimension. But his one is only, it has the dimension in it. And so something funny happens to this scaling law as a function of dimension. Plus, his scaling law relates thermodynamics and correlations. So I said, well, look, your scaling law is the best one of all. And he said, no, there's something funny about my scaling law. I don't want to talk about it. So he didn't, and we never did. But as we'll see later, this scaling law, it really is fundamentally important in the renormalization group theory of phase transitions, which we're going to get to. It relates to something called hyperscaling laws. And it's the fact that it's dimension dependent was even at that stage, at that time in the 1960s when he derived this, it was, I think he derived it in like 1968 or something like that. It was one of the first indications that critical phenomena are very different as you vary the spatial dimension. Anyway, so I'm letting you have that anecdote. And I think I'm not going to start the next topic, which is a renormalization group. So I think we're done for today's lecture. So let me turn off the recording and